This is the fifth video on the spacetime algebra, and in this video I will be covering gradients, specifically their tangential and orthogonal decomposition, how that relates to the relative decomposition, how you can derive the D'Alembert, which is just the square of the four gradient, and then I will be looking at different types of field derivatives, and so we can get an intuition for how uh, fields behave under the gradient. So first, the foregradient. So the foregradient is defined as follows. Foregradient is defined as nabla or del, the sum of all the components gamma superscript mu partial mu. So this is the traditional definition for the foregradient. And this can be decomposed or restricted to, I'll just say decomposed. It can be decomposed to tangential and orthogonal directions. And orthogonal directions along any multivector M. Any multivector M in the STA. And what this looks like is del equal to del the tangential gradient and the orthogonal gradient, where this is taking the derivative on the surface of this multivector M, and this is taking the derivative on the, or like directly orthogonal to this multivector M. So like if this were a vector, then this would give the rate of change along the vector. This would give the rate of change in the plane orthogonal to the vector. So let's look a little bit more at what these actually look like. So you start with just nabla del, and that's just equal to the multivector's inverse times the multivector itself, which is the same thing as, because this is an associative algebra, same thing as just multiplying these two together first. And if you expand out the geometric product, you have m dot del plus m inverse m wedge del. And this implies that the tangential derivative or gradient is equal to this, which just looks like a projection. Like this just looks like the projection formula. And you have a similar one, which looks like the rejection formula. Right here. So that's the form of this, is this. And this gives the relative decomposition of the gradient. The relative decomposition And the relative decomposition is going to look like this. We're going to have you can have del equal to gamma naught squared, because gamma naught squares to 1. Gamma naught. Then expand this out. And you have this right here. Well, this actually implies that the projection or the tangential derivative, so what's changing in time, is gamma naught, gamma dot, this, which ends up being equal to, which just ends up being equal to gamma naught partial here. And this would be the component that's in, or this would just be the time component if you were dealing with paravectors. And this also gives the orthogonal, which is gamma naught wedge del, which is equal to gamma naught, and then the three gradient. So this is this right here is the 3 gradient, where you sum over j of sigma superscript j times, what's it called? This. So that's what you end up with there. Well, this implies we can then rewrite the 4 gradient as gamma naught, the partial of the time direction, plus the 3 gradient, which is equal to this version here. So because the gamma commutes with the partial here, but it anti-commutes with this 3, with this 3 gradient. So the 4 gradient can be decomposed in terms of the 3 gradient and spatial or time derivative. And so then we can look at the D'Alembertien. D'Alembertien, which is defined as the square of the 4 gradient, but we can just multiply these two forms together because they're equal to each other. So we have partial this gamma naught, but then it's times this gamma naught. So we end up with gamma naught squared, which ends up just being partial times squared minus the 3 gradients squared, which this is the traditional D'Alembertien definition. So we can see that squaring the 4 gradient does indeed give the D'Alembertien. Now let's look at field gradients. there is a general pattern. So if you have so 1, 2, 3, 4, 5. The reason I write out 5 is because if you have a scalar field, then you have a vector field, and then you have a bivector field, then you can have a trivector field, and you can also have a pseudoscalar field like this. So these are all elements. So for example, this one will be an element of R. This is STA. I'm going to copy and paste this. So this is 4, 3, 2, 1. Well, if you take the gradients of each of these, you have the gradient of alpha of x, which creates another field, gradient of the vector field, gradient of the bivector field, gradient of the trivector field, and then the gradient of the pseudoscalar field. I'll end up with these. Oh, copy. These all end up being equal to, this ends up being a vector. The gradient of the vector field ends up being a scalar and a bivector. The gradient of a bivector field gives a vector and a trivector. Gradient of a trivector gives a bivector and a pseudoscalar. And the gradient of a pseudoscalar gives a trivector. So you have this basic behavior here. And so there's a pattern, and that is that, so if you have a field that is an element of the even subalgebra with the field, then the gradient of that field is in the odd subspace. And likewise, if you have something in the odd subspace and you take its gradient, then that'll be in the even subspace. So the odd and the even subspace are dual under the action of the gradient. But it gets even more interesting. Let's consider the complex structure. So let's say we have a complex scalar field. So complex scalar field. So that complex scalar field is going to be lambda of x, and it'll be in the 0 plus 4 subspace. Well, then its derivative or its gradient here, the gradient of this complex scalar, is a complex vector. So it's a complex vector, meaning that the gradient of this is a vector and a trivector. So let's look then at a complex vector field. We have a complex vector field, then say that's z of x in the STA 1 plus 3. Then the gradient of this vector field, or this complex vector field rather, is an even element. Meaning that the gradient of this field right here is equal to a scalar plus a bivector plus a pseudoscalar. If this is normalized, then that means that the gradient would produce a rotor. And finally, we can look at the bivector field, which the bivector fields have complex structure. So you don't need to say complex bivector field because the bivectors are naturally complex within the spacetime algebra. So if you have bivector field, then the gradient of this bivector field is also a complex vector. So because both bivector fields and complex scalar fields give complex vectors, then you can define this as an even, you can say that there's an even field. So the spacetime algebra paper that we're working out of calls this a spinor field. However, this is not a spinor field because it's not a field of a minimal left ideals. It's a field of even elements of the spacetime algebra. So I will be calling it an even field. So if you have an even field, and we'll write that as t of x, and we can just call that lambda of x plus f of x. It has a complex scalar and a bivector component. Then the gradient of this field, of this even field, is a complex vector. Which this right here is saying the exact same thing as this duality here. This a of x is equivalent to this c of x. And then the result here that this complex vector field gives an even element is the same as this right here. So let's consider just the canonical form of a bivector, just to see how phase factors interact with the gradient. So consider the canonical form of a bivector. So f of x is equal to e to phi, which depends upon x, and then say that there's some global phase, and then little f of x. So this is called local phase because the phase here changes at every point on the spacetime manifold. And this is called a global phase because it is constant throughout the entire manifold. So a global phase and a local phase. And then, of course, you have the canonical form of the bivector itself. So if we have that, this implies that therefore the gradient of this field is equal to, you just have the phase vector, and then the gradient of the canonical bivector plus the gradient of the phase times the original bivector, capital F, and the pseudoscalar. And then this term here comes from the gradient of e to the phi of x I plus phi naught I. This is constant, so when you take the derivative of this, it's just going to end up being phi times phi of x plus phi naught I. But this goes away, so you end up only with this. Hence why, or you end up with that, but there's also this, you get all of the stuff up here, phi of x plus phi naught. You get all of that. So that's in this, and that's why this is still remains there, and you would still have the canonical decomposition, so you can just represent it as the total bivector f. Then you have the I from that, and then the gradient of the local phase. Let's look at field gradients.